Okay, this is another video in the series for Math 1073 for UTSA. We're going to be dealing with Module 2.2, domains and ranges of functions. There are several parts to this one, and we're going to be finding the domain of each function using interval notation. Let's look at our first example, f of x equals 7x plus 3. So basically, this function, you pick an input, multiply by 7, add 3, you get a result, right? So when I'm thinking about this, I know that in the past, an equation like y equals 7x plus 3, that was a linear equation. I make a straight line, right? So if I'm thinking about what it looks like, well, it's a straight line, and x could be anything. Or in other words, if I look at the formula, because sometimes we're not going to know what the graph looks like, we need to go based on the formula only. I can multiply anything by 7. If x, x can't be 20 because 20 minus 7 doesn't, 20 times 7 doesn't work. Well, no, that's not going to happen. No matter what I pick for x, I can always multiply by 7. I can always add 3. And this similar idea will be true for any linear function. If 7 were 17 or 37 or 87, that doesn't affect which x values are allowed. Okay, so the domain here is going to be all real numbers. So the problem says to use interval notation, so I'll do that. So negative infinity to infinity. And this just basically means, like on a number line, if I think about putting 0 at the middle and I have arrows on both ends, infinity is not a number, but I can think of infinity as being all the way at the end on the right and negative infinity as being all the way at the end on the left. So if I say, okay, start at infinity, that's what the first guy means, right? Start here and then end here. That means basically run the gamut of the entire number line, cover everything. So that's why we write negative infinity to infinity for an interval meaning all real numbers. So sometimes it'll be okay to write the words all real numbers. For example, in WebWork, that won't work, right? Because you type that in, WebWork goes, oh, this is all is not defined in this context, right? So all real numbers, literally, that's what the interval notation here that I'm using refers to. It's just other notation. There's another symbol for this. If you make like a capital R, but you make the vertical line twice, okay, this is called, sometimes this is called blackboard bold, or it's called a double struck R. This is another kind of notation meaning all real numbers. So each of these three things literally means the same thing, has the same concept, but, WebWork wouldn't, like if you just type in capital R into WebWork, it's not going to recognize that. So WebWork is going to always want interval notation, which is why in this video, we'll be focusing primarily on interval notation. When you get to pre-cal and cal 1, there'll be times where this is convenient, but in this course, we'll focus on interval notation. And maybe from time to time, I'll point out other ways to refer to things. Oops, not overzealous with my undos. Okay, so let's look at the next one. So here I have a quadratic, what's called a quadratic function. You might recognize that term, and you might know that from somewhere else. Basically, because I'm squaring, this is called quadratic. Anyway, if I know what the graph looks like, that helps, but let's assume that I don't know what the graph looks like. Basically, I'm going to think, okay, are there any x numbers I can pick? Don't work. They cause some sort of problem. Well, I can square any number, right? You can square any positive number. 7 squared is 7 times 7. 7,000 is 7,000 squared. 7,000 squared is 7,000 times 7,000, or 49 million, right? You can square anything. And x could be 0. 0 squared is 0. X could be negative. You can square a negative, right? Negative 8 squared would be 64, right? So there's no number that I can pick that doesn't work. And then, of course, you can multiply 6 against any result. And then that you can always subtract into 7 or subtract from 7. So no matter what I pick for x, anything will work. So again, my answer is all real numbers. Negative infinity to infinity being the interval notation for that. Okay, let's go look at part C. Now this one might look more complicated, and in some ways it is, in other ways it's not. I'm going to look at this first factor and think, okay, is there anything, assuming that these two guys work out, is there anything, sorry, my undos made that unclear. Assuming these guys work out, ignore them temporarily, pretend that we just have a number here. Is there anything I can plug in for x that would cause a problem? Would 2 times x be problematic? And well, no, you can double any number, right? So this factor is not going to cause an issue. If I look at, say, this factor, and ignoring the other ones temporarily, assume that they're fine, that each of the other factors is just some number. Is there a number I can pick where you can't add 1, or that after adding 1, you can't then multiply this with the rest of the expression. Well, no. Supposing 2x is some number, the x in the first factor is cool, and the x minus 6 is cool, then x plus 1, you can add 1 to whatever you plug in, and then whatever that result is, you can multiply against the other stuff. So there's no problem here. And if I look at x minus 6, assuming the other factors are fine, is there a number that you can't subtract 6 from? Well, no. Subtract 6 from any number. Is there a number that you can't subtract 6 and then multiply the result against something else? Well, no. You can multiply any two numbers. So I'm examining these different factors, and as long as each factor on its own doesn't cause an issue, the product of the three factors, or four, I suppose, if you want, doesn't cause an issue. So again, my domain is all real numbers, negative infinity to infinity. I can plug in x, I can have x just as a multiplier, I can add 1 and then multiply it, or I can subtract 6 and then multiply it. And any x value will work fine with that. Okay, so let's look at the next one. So now, here's where we start getting things that are interesting. We have a square root, right? And you might remember when we talked about roots previously, you can't have an even root of a negative number. In pre-calculus, we'll talk about imaginary numbers and complex numbers, but I believe in this course that it's not covered in this course. It's covered in, it's either, as I've said in a previous video, it's either later in this course, towards the end, or it's in another course entirely. So what that means is the inside of the radical symbol, called the radicand, can't be negative. The radicand, let's spell things correctly, can't be negative. And this is true whenever the index is even. The radicand can't be negative if the index is even. What index? What is that? Well, the index of the root. This is a square root. And so there's nothing written here in this little gap, right? If we had a cube root, we'd have a 3. If we had a fourth root, we'd have a 4. Another way to write this would be 5 times root symbol. Oops, the auto line tool wants to help out. We'd put a little 2 if we want to be more explicit. The index goes in this little pocket, right? But for a square root, we don't bother writing the 2. We don't need the 2 necessarily. So the radicand can't be negative. So I'm going to set x plus 2 to be greater than or equal to 0. I'm going to set up an inequality to describe which numbers are allowed. And now I just have to solve the inequality. So I can subtract 2 on both sides and get x is greater than or equal to negative 2. And this is an inequality that describes which numbers I have allowed for the domain, right? So this will be all numbers that are greater than or equal to negative 2. Again, our answer needs to be in an interval form. So I'm going to say that my interval solution is bracket negative 2 to infinity. And to clarify, to make sure everyone's okay with this, I'm using a closed bracket because I have greater than or equal to. So negative 2 is a solution to the inequality. Therefore, negative 2 should be included. Another way to see this, or to say this, is say, well, what's f of negative 2? Well, that's 5 times the square root of negative 2 plus 5, plus 2 rather. And some of you might say, oh no, we got a negative, that doesn't work. But we have to resolve the radicand, simplify it first. And we get 5 times the root of 0, square root of 0. And of course, the square root of 0 is 0. So 5 times 0 equals 0. So we get a result from this negative 2 input, meaning negative 2 is in the domain. If I had made an error up here in my inequality and I had chosen to do like x plus 5 is greater than 0, then I would have mistakenly excluded negative 2. Anyway, so whenever you have a radical, you need to think about, are negatives allowed? And if not, and we'll get to an example where it is, if not, you need to set up an inequality. I shouldn't say you need to. It's one way to do it. Okay. Another way is to say, well, what would I plug in to make the radicand 0? And that's where my interval will start or stop. But you might have a more complicated example where you do need to write this out. You might look at this and go, I don't need to write all that out. I see what the answer is. Okay, that's fine. Sometimes, though, you might need to write things out because the radicand's more complicated. And as I probably alluded to, the radicand can't be negative if the index is even. If the index is odd, then the radicand can be negative, which I suspect is our next example. Yeah, so now our index is odd. Index is 3, the cube root. And you can have the cube root of a negative. So like if I were to plug in, say, 1, what's h of 1? Not f, h. What is h of 1? Okay, well, that's going to be the cube root of 1 minus 2 times 1, right? 2 times 1, of course, is 2, so 1 minus 2 is negative 1. So this is the cube root of negative 1, which is, of course, negative 1, right? So that's allowed. The radicand can be negative. So when you have an odd root, you don't have to worry about plus or minus in the radicand. So all I need to confirm is, will the radicand accept any input, right? Will any number work to plug in? And inside, we basically have a linear expression, 1 minus 2x. Could be rewritten as negative 2x plus 1 if you wanted. So the inside, the radicand is essentially linear. So yeah, it accepts anything. And the cube root doesn't have any problems. It doesn't reject anything. So yeah, for this one, the domain is all real numbers. Okay. So let's go to the next one, which might be the last one. Nope, it's not the last one. So this one is a little bit harder. This is more complicated because we have both a fraction, we have a rational function, right? And we have a root involved. Since we cannot divide by 0, this denominator, if we plug in 9, we're going to have a problem. F of 9 is undefined, right? If I say, oh, well, what's f of 9? F of 9, well, this is going to be the square root of 9. The AutoLine tool is again trying to help. 9 minus 4 all over 9 minus 9. And we get root 5 over 0. I'm hesitating to write equals, and I'll see why in a second. Square root of 5 over 0. But you can't divide by 0. That doesn't work, right? I hesitate to say equals because we're going to get a nonsensical expression. What does it mean for them to be equal? If root 5 over 0 is undefined, how can it equal anything? So I'm abusing the notation a little bit in this case. This kind of thing will become more important in Cal 1. Like, how do you handle division by 0 will be treated a little bit, well, a lot more depth in Cal 1. So, that's basically something to think about. 9 is not a valid input because of the denominator. Now, in the numerator, oops, changed my tool here. In the numerator, the radicand can't be negative. We have an even root, so x minus 4 must be greater than or equal to 0. Okay, so I can solve that by adding 4 to both sides. So x is greater than or equal to 4. Okay, so x must be greater than or equal to 4. Sorry, x must be greater than or equal to 4, but x can't be 9. So I think it might help to put this on a number line, and then we'll make the interval. So I'll mark down 4, say here. I'll mark down 9, say here. So 4 is included, 9 is not. So I'll put an open circle around 9. And then everything between 4 and 9 is included, like 5, 6, 7, 7.5, 8.3. And then everything after 9 as well. Okay, so like 10 would be in the domain. Now, as an interval, basically, I'm going to have to use a union of 2 intervals because this first section from 4 to 9, that's an interval from 4 to 9. So I'm going to have a bracket 4, because I'm including the 4, right, up to 9, parenthesis, because I'm not including the 9. And then I have a second interval from 9 to infinity. So I'm going to do a union, okay, 9 to infinity. And I'll observe that this is not the letter U. So not U, it's the union symbol. It's sometimes called the cup symbol because it's like a cup with, say, no handle on it. Anyway, that's the domain for that function. So this is a little bit harder because there's 2 things we had to look out for. We had to look out for division by 0, and we had to look out for a negative radicand in this case. Okay, let's go look for this one. This one, the numerator is just a linear function, x minus 1. So the numerator is not going to cause us any issues. X could be anything as far as the numerator is concerned. The bottom, however, the denominator, since we can't divide by 0, we look for when is this 0? And then those values will get excluded from the domain, okay? So I'm going to set up an equation and say, okay, when is this 0? 0 equals x squared minus 2x minus 63. And some people will put like a line through this. 0 is not equal to, because you're looking for where the domain includes the values where the bottom isn't 0. I prefer to say, no, I'm looking for where the bottom is 0, and then separately I'll exclude them. And whether you call this equals or not equals is sort of subjective. As long as at the end you're excluding the right values, that's fine. So this one factors, and I'll assume everyone's okay. I notice that the 63 is 7 times 9, so I can say this is x minus 9 times x plus 7. If the numbers were not so kind, I might have to go through some more effort to solve this, but these numbers were chosen to be relatively straightforward. So I can basically separate the two factors and say, oh, well, that means 0 equals x minus 9, or 0 equals x plus 7, right? I'm using the zero product property. And so in this first equation, I'll add 9 to both sides. So 9 equals x. In this equation, I'll subtract 7 on both sides. So negative 7 equals x. So those are my two values where the denominator is 0. Therefore, they're not in the domain. Okay. I'm going to do this number line approach again. Not that you actually have to draw out a number line to make the interval, but I think it's helpful to illustrate. So I'll mark out negative 7 and 9. And make sure to put these in the right order. Of course, negative 7 is on the left because it's negative. Of course, negative 7 is less than 9. So I'm including everything but not those two. So I'm going to put an open circle around negative 7 and an open circle around 9. And then I'm including everything else. Everything else will work. It's like 0, 2, 10, 35, negative 8,000. Those all work. And so for this first chunk, I need to write out that interval first. So negative infinity up to negative 7. Okay. Union with this next chunk, negative 7 up to 9. And in each case, I'm not including those numbers. That's the whole point. We're excluding them. And then 9 to infinity. Okay, so there's the domain for that function. Okay. You might wonder, well, what if the bottom had a higher degree, like it was x cubed or x to the 4th or x to the 5th or whatever? I'd have more chunks, right? Yeah, you'd have more numbers excluded potentially. So you'd have more chunks in your domain, more intervals that are unioned together. And there is other notation. I'm hesitating to point it out, but I'll go ahead and say, okay, WebWork will not accept this, but here's other notation. So WebWork won't like, won't like this. But this is other notation that you will see in probably in pre-cal and Cal 1. So you can say this double struct R, remember that means all real numbers, minus, and then this curly bracket, I can put the negative 7 and the 9 and close the curly brackets. What this says is this minus, it's not subtraction, like, oh, I need to distribute plus 7 and minus 9. No, it's different because this is called set notation. This means take this first group, the real numbers, and remove from that group these two numbers. And then the rest is the numbers that we're talking about. Or the rest are the numbers that we're talking about. So this notation means the exact same thing that the interval notation does. But for whatever reason, WebWork is going to only want interval notation. I don't think WebWork has the capacity to take this notation. Like, even if we wanted to have the problems accept this version, I don't think WebWork could do that. I could be wrong, but I don't think that it could. Anyway, this is something you'll see later in pre-cal and cal 1. So seen in 1093 and 1214, etc. later courses. Okay. From time to time, I'll try to inundate you with things that you actually don't necessarily need right now. But at times, I think it's a good idea to point out, okay, this is notation you're going to see later. And for some of you, you might, when I showed this, go, oh yeah, I remember that. I saw this in algebra in high school or whatever. And I'm just reminding you, yeah, this is a thing. Just we're focusing on this notation for this course. Okay. So this one is a lot like the one north of it, this one, except now the bottom is where the radical is. So the numerator, and you know what? We forgot to label this with a function. So what comes after g? E, F, H, G. Let's go with j. Let's say this is j of x. I don't think we used that. Okay, j of x. So the top is fine. The 7, the 7 just sits there. There's no x. There's no variability. So the numerator is just fine. In the denominator, though, we got something to think about. The radicand can't be negative. We have an even root, right? Can't be negative. Can't be less than 0, right? But also, since we're dividing by the radical, can't be 0 either. So x minus 9 is greater than 0. Because if we plug in, I'm sorry, if x minus 9 is 0, then we would be dividing by 0. So that's not allowed. So I can solve this inequality and get x is greater than 9. So I want everything that's greater than 9. I won't draw a number line this time. But if I want to say everything greater than 9, then I start my interval at 9, not including it, and go up to infinity, because that will include everything greater. And if you think about it, just to check, well, what's j of 9? J of 9, well, this is 7 over the square root of 9 minus 9. And again, I'm hesitating with this equal sign. Well, that's 7 over 0, and that doesn't work. You can't divide by 0, which is why we're excluding 9 in the interval. Also, I should point out, since we're talking about, at some points, what WebWork likes and doesn't like, of course, I don't know about you guys, but I don't have an infinity key on my keyboard. So, of course, WebWork wants you to do the following. I would type in parenthesis 9 comma inf, right, for infinity, because there's no infinity button on the keyboard. So if we backtrack a little bit and go look at, say, the first one, right? What WebWork is going to want WebWork wants parenthesis negative inf comma inf. And I'm pretty sure that you could also type out infinity, the whole word, but inf should be accepted. What you should not do is on a benchmark write one of these. Just write the infinity symbol. The infinity symbol. Don't write inf or infinity in a word. Use the symbol for infinity on a benchmark. So let's go look at the next one. Okay, so now we're going to look at finding domain and range when we have a graph. When you don't have a graph, you just have a formula, f of x equals whatever. Range can be very challenging. That's something we'll deal with later for specific types of functions. So looking at this graph, okay, remember that typically the domain will correspond to the x-coordinate, or to the x values that are used, and then the range will correspond to the y-coordinate, or to the y values that are used. So if I look at the horizontal space that this graph covers, it goes from -5 up to 3. Okay, and notice that at 5 we have a filled in dot. So that point, -5 comma 2, is actually used. That's part of the graph of the function. So -5 is an input. Okay, at the other end, notice that there's an open circle, meaning that that ordered pair 3 comma 2 is not part of the graph. So 3 is not included in the domain. So looking at that horizontal spacing, that tells me that the domain, that this is going to equal, let me change colors here. Yeah, let's do that. The domain is going to equal the interval from -5 up to 3, not including 3. Okay. Now, when I go look for the range, I'm looking at the vertical component. What vertical space is covered by the graph? So basically, it's from 0 up to 2, okay? And at 0, I can look on the graph and look at that low point, the bottom of it's like a bowl. At the middle or bottom of the bowl, the graph touches the x-axis, so there's an x-intercept there, right? Now, there's no dot, as in it's not filled in like that, but we couldn't have the entire graph made up of dots like this. So wherever there's a smooth piece of graph, like this one, it just goes, it's a curve. That's implied that if we wanted, we could put a dot there. We just don't do that typically in the middle of a smooth part of the graph, because otherwise it would just be this thick sequence of dots, and we don't want to do that, because then, I don't know, it's just cluttered. It's nicer to have a smooth curve like we have here. So 0 is part of the range. There is a point on the graph with y-coordinate 0. Now, the other end of the range, 2, you might notice, oh, that's a problem, because 2 does not get used as an output value because there's an open circle there. But actually, 2 does get used on the other side. Okay, so 2 is an actual output. When -5 is the input, 2 is the output. When 3 is the input, well, there is no output that's not in the domain, but this being an open circle here doesn't interfere with this being filled in here. So 2 is in the range. So the range for this one will be 0 to 2, inclusive on both ends. Okay, so let's go look at the next example, this graph. Okay, so for this one, remember, the domain is the horizontal axis, the range is the vertical axis. Okay, that's the way graphs are typically done. Not that you can't have an alternative. Oh, could you have it to where the range is the horizontal and the domain was the vertical? I suppose we just typically won't do that. So if I look for the domain, well, what's covered horizontally? Well, -4 up to, I guess this arrow means we continue to the right. Okay. So -4 inclusive because of this dot up to infinity, essentially. So the domain, this will be -4 up to infinity. Now, how about the range? So I'm looking at the vertical axis. Well, we're starting at -2 and we're going up. And where do we stop? Well, you might say, well, this sure looks like it flattens out. Like, does the curve ever reach +4? Does the curve keep going up, or does it flatten out? You might think, well, that's not very clear. Well, if it were to flatten out, then the graph, say it flattened out at 4, right? And it never reached 4. Then the graph would need to include what's called an asymptote. Oh, there's a dashed line indicating that that's an asymptote, right? That's what should be there if that were the case. That doesn't happen. The graph just has an arrow and keeps going. So based on the way this is drawn, we're going to assume, because the graph doesn't tell us otherwise, it can be problematic to say that we're going to assume. Well, then how do I know what to assume? Well, we're going to assume that the graph keeps traveling with the trajectory it has at the end, unless we're told otherwise. If this thing is supposed to curve down, then the graph should have more horizontal space, and it should include that. If the graph, we're going to do anything other than what it appears to be doing here, well, then there should be some more dashed lines, some more grid marks, and it should show more and show us what's going to happen. So you basically look at what's the current trajectory, and you just kind of assume it's the rest is the same. Otherwise, the graph would show you more. So I could say, well, vertically, that red section just keeps going up, right? Just because the graph doesn't include any here doesn't mean that's not part of the function that's implied. It's implied that the graph is going to keep going up over time. Okay, and maybe you have to go really far out to the right to get y equals 5 or 6 or 7, but it does it eventually. So we're going to say that the range is -2 inclusive to infinity. Okay, so let's find the next example. This one is much like the first one, but it's bowed out differently. So wouldn't be a bad idea for you to pause the video and think about, okay, what's the domain here? What's the horizontal coverage? So horizontal coverage, -4 to 4. There are closed endpoints. So the domain is -4 to 4. Okay, that's fairly straightforward. How about the range? Well, what's the vertical coverage? Well, from 0 to 2, much like the first one. I think the first one was 0 to 2. Yeah, it's very similar to the first one. And there are no open circles, so we're going to include 0 and 2 in our interval. Okay. What about the next one? Now this is a good one. So, what is the horizontal coverage? Well, if I'm thinking about starting from the basically like when I'm drawing out my horizontal coverage, right? I want to start as far left as possible just because I want to draw it in one motion. And I notice that we have an open circle here, which means that's where the graph begins. If you're looking from left to right, as we typically read, we can say, oh, well, the graph begins there. Okay. If you're looking from right to left, which at times we'll want to, you can say, oh, well, the graph ends there. It's beginning versus ending is a matter of direction. Where are you coming from, right? So I'm going to say, I want to draw a, I want to mark that location on the axis. I'm going to use my straight line tool, make a vertical line going straight down. So it looks to me like negative 2.5 is where the domain starts. And then this arrow implies that the graph keeps going as it appears to go up and to the right. So keep going like this, and it's moving to the right as it goes up. So I'm going to cover that horizontal space. I'm going to cover x equals 4, 6, 8, 10. As long as I have enough vertical space to keep drawing out, I'm going to assume I follow the same trajectory, okay? Which is not really an assumption. The graph is saying, oh, this is the path we're taking. And if it was supposed to say, no, it's going to stop here, well, then it should put a dot and say that we're stopping. The arrow means continue, okay? So my domain is going to be from negative 2.5 out to infinity, okay? I'm following the trajectory that is implied by having the arrow. So negative 2.5. And on WebWork, you would be able to zoom, depending on how the graph is made, you should be able to zoom in a little bit and get a better picture. There's a couple of different tools in WebWork that will show you a graph. Some are static images, some are zoomable. So if you can zoom in and you want to go, oh, I really need to zero in on what this value is. But I think that negative 3 would be like right there. And so negative 2.5 is about where that mark is. So I'll go with negative 2.5 up to infinity. Okay. Oh, and that's the domain, of course. So now range. Now this is a little bit harder. At the bottom end, we're starting down here at negative 4, including, and we're going up. Do we stop at 10? Well, no. This arrow means we're continuing that trajectory. So although this side doesn't go above 10, this side does. So we just continue up to infinity. So the range is going to be negative 4 inclusive up to infinity. Okay. And as I said earlier, in WebWork, of course, you don't have an infinity button. So you could say negative 2.5 comma inf, or for the range, negative 4 comma inf. Okay, so that's basically how you determine domain and range based on a graph.